All right, I want to talk about categories of equilibrium. In the last video, we wrote the equations for equilibrium, and these are the general equations. So the sum of forces in the plane, so that's two directions, has to be 0, and then the sum of the moments about any point, and really it's about an axis perpendicular to this plane that's passing through a point. So some of the moments about any of those has to be 0. And so this gets fleshed out in a couple of different categories because we can have different kinds of loads that are easily identified. So the first force system to consider is that of collinear forces. And so a free body diagram of that would look something like this. So F1 and F2 and F3 are all collinear. And so you would set one of your axes, in this case it's the x-axis, along that direction. And the only equation that you would need to consider is the forces in the x being equal to 0. And the reason for that is, well, your y-axis would be perpendicular. There are no forces in the y direction. So that one is satisfied by default. And if you took a moment around, say, a point on that line of action, well, every single force goes through point O. So the moment around point O would be 0 by default. So it doesn't do you any good to consider all three equations. You really only need the one. The second category is that of forces which are concurrent at a point. So point O is shown here, and we have F1 and 2 and 3 and 4, and they all intersect. Well, for this one, what happens is your independent equations cover the force summation in the plane. So forces x equals 0 and the sum of the forces in the y equals 0. But because all four forces are concurrent at O, then sum of the moments around O equals 0 is already satisfied. So it won't do you any good to write that equation somewhere else. That's why it says independent equations. You can write this. You could certainly say, well, let me take the moment around A, but it's not going to be a useful equation. Like this equation will be a combination, some combination of the other two. It won't be independent, so it's not really that beneficial. All right, the third system would be that of parallel forces. So you can see F1, 2, 3, and 4, they share the same direction in space. They're all parallel, so their lines of action are all parallel. But they don't have the same line of action as they did in case number 1. So here, you can establish your coordinate frame, and you'll notice that forces in the x has to be equal to 0. That's useful because the forces are all in the x direction. It is not useful to some forces in the y direction because nothing points in that direction. So that's not a useful equation. It just isn't. But it would be useful to take moment around a z-axis that passes through some point wherever you want to take it. That would be useful. Now, in general, as was already discussed, this is the introduction one that we did at the top. You have a combination of forces that are neither collinear, concurrent, or parallel, and you may even have applied couples, in which case you're going to need all three equations in order to solve it. Now, I want to point something out, and we didn't talk about it in the last video, and I did so by default because I wanted to get into these figures. You only have three independent equations at most. So you can't write any more than that, no matter what you might think. And this is where this shows up. So let's say on this figure here, let's say you don't have enough equations. So maybe there's 4 unknowns. Well, you have a problem if there are 4 unknowns, because I've already said you only have 3 independent equations. So what people will do, they'll say, well, I'll take a moment around A, and then I'll take a moment around B. So I'll do some of the forces in the x equals 0, I'll do some of the forces in the y equals 0, I'll take some of the moments around A equals 0, and I'll take some of the moments around B equals 0. Here's the problem. You can only have 3 of these. So you could either take these 3, or you could take these 3, or you could take these 3, or you could take these 3. But you can't take all 4. And what will happen is the fourth equation will be a linear combination of the other three. And so this gives us a very important point. If you only have three independent equations at most, then you can only solve for three unknowns at most. If you have more unknowns, so if greater than three unknowns, you just need more equations. And they're going to have to come from either information in the problem statement. That's a commonly overlooked place. Or another free body diagram. If you draw another free body diagram, you will get three more equations that you can write. And it's possible that will help you. Now, we're in two-dimensional equilibrium, so this isn't a big deal right now. But later in the course, we're going to see this become a problem. So, you can't cheat the system. You only have three independent equations in two-dimensional equilibrium for every free body diagram that you draw. All right, so those are the categories of equilibrium with a comment about the number of valid equations and unknowns. All right, we'll stop there.